In this video, we want to take a look at a slightly different type of improper integral, one that's not quite as obvious and when you first look at it as the ones where you have one of your limits of integration being infinity. So this is when we have one of our limits of integration, being an asymptote, or we can also look at this even further, which we will do in class, of what if there's an asymptote inside of our interval that we're integrating over. So we're going to just kind of look at a small piece of that right now in this intro video and look at the integral from 2 to 5 of 1 over the square root of x squared minus 2. And hopefully just from looking at that equation, we should know that there's an issue with 2 because that is an asymptote for this function. It gives us 0 on the bottom of this fraction, and I drew a little quick picture of this function from 2 to infinity. I drew in the asymptote there as well, but we're looking at it from 2 to 5, and so we're looking at this area here and wondering, again, is this a finite area? Or because we've got this asymptote, which keeps getting closer, our graph keeps getting closer and closer to that asymptote, but not, fully touching it, is that adding enough area so that this area just keeps getting bigger and bigger without any bound on it? Or is this one where it is going to, converge to a number like we saw a couple times on the previous video? So what we want to look at is what's happening to this as we get closer to 2. So we're going to put on here a limit as x goes to 2, but we're going towards 2 from the right-hand side. So this is going to be a right-hand limit. It's probably been, again, a little while since we've seen these. So we're going to get, the idea is that we're taking the t, sort of in these positions, going closer and closer to 2 and looking at what happens for those sort of various values of t as we get closer to that. So we're going to take the integral with t as our limit of integration instead of 2. So we're going to have t to 5 of 1 over the square root of x minus 2 dx. Technically with this one, we're going to need to use substitution, but du is equal to dx, and there's no funny coefficients that we need to deal with. So I'm also not going to change the limits of integration because I really don't want to. So I'm going to write them that x is equal to t and x is equal to 5 so that I remember that I didn't change my limits of integration. And then I'm going to write this as u to the negative 1/2, so I can use that power rule to get u to the 1/2, and then times that coefficient of 2. And again, this is from x equaling t to x equaling 5. So we'll plug back into our square root x minus 2 from t to 5. And then again, using the fundamental theorem of calculus, we'll get that we're going to have 2 times the square root of 5 minus 3. Oh, 2, sorry, my brain worked a little faster there than it should have, and I kept turning things into 3s here. There we go. That should also be a 2. And then minus 2 times the square root of t minus 2. So this simplifies to be 2 times the square root of 3 minus 2 square root of t minus 2. And now we want to look at it with the limit. So I could be writing the limit out in front this whole time on any of these. I just am kind of lazy and I don't like to do that. So usually what I do is kind of wait to the end till I've got this equation for my limit, and then take the limit of just this equation, not have to deal with the integral or any of that kind of stuff. So what we want to look at is that sometimes with these limits, when we get this equation, we can physically plug the number in because we don't have the issue that we're dividing by 0 or anything like that. And that's what's happening here. We can plug in 2 for t. And sorry, both of these on my limits, this should be a t. T is going to 2, not x. There we go. So we get 2 square root of 3 minus 2 times 2 minus 2, so many 2's. But we end up with 2 square root of 3 minus 0, and we end up with 2 square root of 3. So that's actually, again, what our integral is equal to. So back up here, this integral, our area under that curve is 2 square root of 3. So again, we use this variable t as a replacement for that point that we're having issues at. It's a place where we have an asymptote, or it's infinity, a place we can't actually be. And what we're doing with this limit is looking at what happens as we let that variable get closer and closer and closer to that sort of place that we have that sticky point, going out to infinity or getting closer to that asymptote. And again, we're using t just so we can get hopefully that nice closed formula from our integral, and then we can look at what our limit is from that nice closed formula.